Hello, everyone, and welcome to Microsoft Fabric Thursdays Expert Series 2025, brought to you by Uttar Pradesh Power BI Club. I'm truly excited to be here with you today. In this session, I'll be speaking on scaling AI knowledge systems for continuous innovation in cloud engineering, a topic that's close to my heart and one I believe is shaping the future of how we build, scale, and innovate in the cloud. But before we dive into the details, let me share a little bit about myself. I am Mahmoud Nawaz Khan Muhammad, a data engineering professional with over 13 years of experience working across cloud platforms like Azure, AWS, and GCP. I've had the chance to design and lead scalable data pipelines for Fortune 500 clients in industries like finance, insurance, and retail using tools such as Snowflake, Databricks, Azure Data Factory, Talent, DataStage. My work focuses on cloud migrations, data governance, and BI solutions with Power BI and Tableau, helping organizations turn raw data into actionable insights. I'm passionate about solving complex problems, learning new technologies, and building systems that make data simpler, smarter, and more impactful. Please feel free to connect with me on LinkedIn. I'd really appreciate hearing your thoughts and feedback about my work. Your insights and perspectives help me keep learning and improving. With this, the agenda of the topic is we're going to be discussing on knowledge half-life challenge, four-layer architecture, cognitive augmentation modes, real-world outcomes, ethical and governance imperatives, embedding into fabric workflow. Let's start by taking about a concept that might sound a little technical, but is extremely important for anyone in engineering or technology, and that is knowledge half-life. When we say knowledge half-life, we are talking about the amount of time it takes for half of what we know today to become outdated or irrelevant. Imagine learning something new today, maybe a programming language, a cloud service, or a data engineering tool. How long before half of what you just learned becomes obsolete? That's what knowledge half life measures. In the past, engineers could rely on their core knowledge for years. A software engineer who learned a framework could use it effectively for multiple projects without needing constant retraining. But things have changed dramatically. Technology now evolves so fast that what you learn today might only be relevant for a short period. Here's a striking example. Back in 2018, technical knowledge in engineering lasted around 24 months. That's about 2 years. But by 2023, this shelf life dropped to just 9.7 months. What that means is, in less than a year, half of what an engineer knows could already be outdated. Think about that. A cloud engineer working with certain tools last year may already need to learn new services or architectures this year just to stay current. Why does this matter? First, skills and practices are becoming obsolete very quickly. For instance, Hadoop workflows that were popular a few years ago have largely replaced by Spark or cloud native pipelines. A DevOps engineer fluent in Jenkins might now need to master GitHub Actions or Azure pipelines. The tools, the platforms, even the best practices evolve almost constantly. Second, this rapid obsolescence leads to rising retraining costs and productivity loss. Organizations spend millions trying to keep teams up to date. Every new tool or platform introduces downtime, reduces efficiency temporarily, and increases the risk of mistakes. Traditional knowledge management, PDFs, manuals, and old training sessions simply cannot keep up the pace. This slide tells us why knowledge in engineering is perishable and why organizations need smarter, faster ways to manage it. To address this challenge, we'll explore AI driven knowledge ecosystems designed to keep engineers continuously updated, efficient, and innovative. Introducing knowledge ecosystems. Now that we understand the challenge of shrinking knowledge half life, let's talk about the solution knowledge ecosystem. So, what exactly is a knowledge ecosystem? At its core, a knowledge ecosystem is an AI framework designed for continuous innovation. Unlike traditional knowledge bases or static repositories, it does not just store information, it actively ingests, organizes, and contextualizes data, keeping it relevant and actionable for engineers. Think of it like a living system. Traditional documentation like PDFs or internet pages are static. They don't change unless someone manually updates them. But in a modern tech environment, that approach is not fast enough. New frameworks, cloud tools, and AI models appear constantly. Engineers need a system that evolves just as quickly as. This is where knowledge ecosystems comes in. They continuously update themselves. So the knowledge you access today is already aligned with the latest advancements, best practices, and technical insights. One of the critical principles is resilience. Knowledge ecosystems are built to withstand changes in the underlying technology landscape. Even if a cloud surface, database, or a AI model evolves, the system can adapt and reorganize information automatically. Another principle is low latency access. With this, engineers can retrieve the right insights and almost instantly without digging through multiple tools or dashboards. The system is also platform agnostic. While it can leverage specific capabilities like Microsoft Fabric, it's designed to operate beyond a single vendor or environment. This means it can integrate across multiple cloud platforms, enterprise applications, and tools, providing a unified source of truth. This is helpful because engineers and technical teams spend a lot of time searching for information, trying to figure out whether their approaches are up to date. With the knowledge ecosystem, you are not just retrieving the data, but you are getting context rich insights which are prioritized and tailored for your role. It reduces guesswork, minimizes errors, and speed up decision making. To put it in another way, knowledge ecosystems are like a personal assistance for your technical knowledge. They don't replace engineers, they amplify their ability to innovate, make decisions, and focus on high value work. Instead of sifting through dozens of manuals or outdated notes, the system surfaces what's important, highlights connections between concepts, and keeps teams aligned with the latest technical standards. Architecture overview. Now that we understand what a knowledge ecosystem is and why it's needed, let's dive into how it's structured. The architecture overview gives us the blueprint for how all the pieces work together to deliver continuous innovation and contextual knowledge to engineers. At a high level, the ecosystem is organized into four layers: foundation, processing, interaction, and integration. Each layer serves a distinct purpose, but they are designed to work seamlessly together. This modularity is crucial because it allows the system to scale, adapt, and evolve without requiring a full redesign every time a new technology or a data source are introduced. Let's start with the idea of modularity. Think of it like building with Lego blocks. Each block has a specific function, but you can rearrange them or add new blocks without tearing down the whole structure. This ensures resilience. If one layer faces heavy demand, fails temporarily, or needs upgrades, the other layers can continue operating smoothly. Next is scalability. In a typical engineering environment, the volume of data, documents, and events can explode very quickly. Thousands of logs and code repositories, documentation updates, and design patterns are generated daily. The architecture is built to handle this load efficiently, ensuring that knowledge flows from raw events to applied insights without bottlenecks. The foundation layer captures raw signals in real time. The processing layer transforms unstructured data into structured insights. The interaction layer delivers this knowledge to engineers through dashboards and conversational agents, while the integration layer embeds it directly into workflows. This creates a seamless flow from raw information to actionable knowledge, which is critical for real time decision making. Another key point is resilience. By separating responsibilities across layers, organizations can implement new tools, analytics models, or AI capabilities in one layer without disrupting the others. This reduces downtime and risk. It also encourages continuous improvement. Teams can experiment with new methods, machine learning models, or visualization techniques and integrate them smoothly. This is helpful because without a clear architecture, knowledge systems become chaotic. Engineers waste time hunting for information, duplicate work, and often rely on outdated practices. By providing a structured, layered approach, the ecosystem ensures that the right knowledge reaches the right person at the right time without adding complexity or cognitive overload. This shows how the ecosystem takes raw events, converts them into meaningful insights, presents them effectively, and integrates them seamlessly into workflows. Each layer has a purpose, but together they create a living, scalable, and resilient environment for technical knowledge. Let's talk about foundation layer. We, this layer is essentially the bedrock of the knowledge ecosystem. It's responsible for capturing raw signals as they happen and storing them in a way that allows fast, context rich retrieval. Event driven patterns. In traditional knowledge systems, updates happen periodically, maybe once a day or once a week. That creates a lag between new information being generated and engineers being able to access it. In contrast, the foundation layer is a event driven, which means it reacts instantly to new signals, whether that's a log entry, a document, a code update, or a support ticket. Engineers get access to the latest knowledge as soon as it's available, which is critical in fast moving environments. The second is vector database for semantic retrieval. Traditional databases rely on keyword searches. The works sometimes and sometimes they don't work, but it often misses the meaning behind the query. Vector databases, on the other hand, store information as numerical representations that capture context and semantic relationships. In practice, this means the system can understand questions in natural language and return relevant results even if the wording doesn't exactly match the source data. For example, if an engineer asks about high CPU usage alerts in Kubernetes clusters, the system can return logs, dashboards, and documentation that discusses similar issues, even if they don't use the exact words high CPU usage. And This layer guarantees fast context-rich access. Speed is critical because engineers don't want to waste time digging through PDFs or old internal wiki pages. They need immediate actionable insights. The foundation layer ensures that retrieval is not just fast but also relevant. So engineers get the information they need in the right context. This is important because as the sensory system of the ecosystem, if you don't capture events correctly or store them intelligently, everything built on top, like processing, interaction, and integration, will be less effective. Even the best AI models or dashboards will fail if the raw data is incomplete, delayed, or poorly structured. In real world application, this layer allows organizations to scale to thousands of events simultaneously, handle massive volumes of data, and maintain relevance in a constantly changing technical environment. Without it, engineers would constantly be working with stale knowledge, which evolves slowly and increase the risk of mistakes. So, in summary, the foundation layer is about speed, context, and semantic understanding. It captures the signals in real time, makes sense of them, and ensures they are immediately available for processing, interaction, and integration downstream. This is what sets the stage for all the intelligence and insights in the ecosystem. Let's talk about processing layer. This is where the magic of turning raw data into actionable insights and knowledge happens. This layer sits directly on top of foundation layer and is responsible for transforming unstructured events, logs, documents, and messages into structured insights. First, NLP and ML converting unstructured data into structured insights. In engineering, most of the knowledge is not neatly formatted in databases. It's in the text logs, error messages, incident reports, design documents, emails, or even chat conversations. On their own, they are hard for humans to parse quickly. That's where natural language processing and machine learning come in. NLP allows the system to understand human knowledge, identify the important piece of information, and convert them into structured format. Think of like tables, graphs, or linked knowledge objects. ML models can then detect patterns, trends, and anomalies across thousands of documents or logs automatically. This layer handles large volumes of data efficiently. Modern engineering environments produce an enormous amount of data every day. A single cloud application could generate millions of logs per day. Traditional systems would struggle to process all of this in a timely manner. The processing layer is built to scale horizontally using distributed pipelines to process high throughput streams without slowing down. It ensures that no matter how big the data grows, insights are generated in near real time. Third, it extracts entities, relationships, and context. This is crucial because knowledge is not just about raw facts, it's about understanding how things relate. For example, if an engineer is troubleshooting a cloud outage, the system does not just show the error message, it can identify which microservice is failing, which users are affected, which previous incidents are related, and what previous solutions worked. By linking entities and mapping relationships, the processing layer creates a semantic network of knowledge. This is what allows downstream layers like interaction and integration to deliver meaningful, actionable insights rather than raw data dumps. This is important because it is the brain of the ecosystem. The foundation layer captures raw sensory signals, but without processing, all those signals would just be noise. The processing layer cleans, organizes, and makes sense of the data, turning it into knowledge that humans can actually act on. In practice, this means engineers spend less time manually reading logs or searching documentation and more time making decisions, solving problems, and innovating. The system surfaces anomalies, highlights relationships, and prioritizes information automatically. The processing layer transforms raw signals into structured insights, scales to handle massive data volumes, and extracts relationships and contexts that make the information meaningful. It's a critical step that bridges captured data and human actionable intelligence. Without it, the knowledge ecosystem would not be able to deliver real time actionable results. Interaction layer. This layer is all about humans actually interact with the knowledge ecosystem. Up to this point, we have captured raw events in the foundation layer and transformed them in struggling and structured insights in the processing layer. But in knowledge is not useful if it sits in the system and is not accessible to the people who need it. That's exactly what the interaction layer solves. Conversational agents and dashboards. Imagine engineers working on complex cloud platform or data pipeline. Without this layer, they'd have to dig through logs, dashboards, emails, and documents manually. The interaction layer provides modern interfaces such as chatbots, virtual assistants, or interactive dashboards that allows engineers to ask questions in natural language and get the answers they need. You could ask which service is causing the current spike in errors, and the system can respond with a clear answer, linking to related logs, previous incidents, and potential resolutions. Personalized access to reduced overload. One of the biggest challenges in engineering is information overload. Systems generate enormous amount of data every day. If engineers had to wade through everything, it would be overwhelming and highly inefficient. The interaction layer solves this by personalizing what each user sees. For example, a DevOps engineer might only see alerts and insights relevant to their services, while a product engineer might see a performance trend for their application. This tailored approach saves time and prevents distraction. It tailors output to user context. Context is critical. The same insight mean different things depending on who is looking at it and what they are responsible for. For instance, a spike in API latency might be a minor issue for a developer focused on testing, but a critical alert for a site reliability engineer monitoring production. That interaction layer understands roles, prioritize, and context of queries to deliver information that is actionable and relevant. This is important because human facing side of knowledge ecosystem, without it, all the data processing and semantic structuring we discussed in the previous layers would not reach the engineers effectively. The interaction layer ensures the knowledge flows smoothly from system to the people in a form they can understand and act upon. In practice, this means engineers can quickly resolve incidents with minimal downtime and access insights without switching between multiple tools, focus only on what matters most, reducing mental load, make faster data driven decisions. Integration layer. This layer is all about bringing the knowledge directly into the workflows and tools that engineers already use, so they don't have to leave their environment to find insights. Knowledge embedded into workflows, engineers spend a lot of time inside their integrated development environments, monitoring dashboards, or ticketing systems. The integration layer ensures that the intelligence generated by ecosystems appears right there within the tools they are already using. For example, if an engineer is working in Visual Studio or IntelliJ, relevant alerts, insights, and recommendations from the knowledge system can appear in a side panel or directly in the code review process. This reduces the need to constantly switch apps or search multiple ecosystems, saving time and keeping the focus on the work at hand. Next, APIs for seamless access. The ecosystem does not operate in isolation. Modern engineering environments are highly heterogeneous. With multiple platform tools and services, the integration layer exposes APIs that allow other systems like ticketing platforms, monitoring tools, or collaboration software to tap directly into the knowledge ecosystem. This means any tool can become smarter, surfacing contextual insights, predictive alerts, or suggestions without engineers having to manually query the systems. APIs essentially make the ecosystem ubiquitous and interoperable, extending its benefits across the organization. Finally, reduces context switching. Context switching is a major productivity killer. Imagine an engineer is troubleshooting a production issue. Normally, they would have to jump between the incident management tool, long analysis dashboards, documentations, and maybe Slack channels to communicate with the teammates. With the integration layer, relevant knowledge comes to them within their workflow, so they spend less time navigating systems and more time solving the problem. This not only saves time but also reduces cognitive load and minimizes errors, causing fragmentation information to be solved. This is matter because integration layer essentially closes the loop between knowledge and action. All the structured insights from the processing layer and personalized outputs from the interaction layer become directly actionable, allowing engineers to make faster, smarter decisions. It also ensures that AI enhanced knowledge becomes part of daily routines, not an extra tool to learn or manage. In real world terms, this layer empowers organizations to increase operational efficiency by providing insights where work happens, improve incident response times, reduce mental fatigue caused by juggling multiple systems, knowledge ensure knowledge is constantly and consistently applied across projects and teams. Real world impact. Let's look at the real world impact of implementing this knowledge ecosystem. This is where theory meets reality, how this system actually changes the way engineers work and organizations perform. Here are the impressive metrics: 18,427 technical documents processed monthly, 93.4% accuracy in insights delivered, 73.6% reduction in overload, and 3.8 times faster solution generation. 18,427 technical documents processed monthly is not just a random number. It represents the scale at which the ecosystem can operate. In a modern engineering organization, there are thousands of new documents, code commits, logs, incident reports. and knowledge artifacts created every month. Traditionally, engineers would have to manually sift through these sources to find relevant insights. That's time consuming and error prone. With the knowledge ecosystem in place, all of this data is ingested, indexed, and processed automatically. So engineers get structured, meaningful insights without the manual effort. This allows teams to handle a high volume of information without feeling overwhelmed. 93.4% accuracy in insights delivered is critical because imagine you are acting on a suggestion or an alert from the system. If it's a wrong, it could waste time or even cause errors in production. Achieving over 93% accuracy means engineers can trust the recommendations coming from the ecosystem. They don't have to send and do second guesses the AI or cross check endlessly, which further speeds up decision making and reduces the chance of mistakes. 73.6% reduction in overload is also huge because cognitive overload is one of the biggest challenges in modern engineering. Engineers are constantly bombarded with logs, emails, monitoring alerts, and documentation. The system filters out irrelevant noise, surfaces the most important information, and presents it contextually. This is not just a productivity gain, it reduces stress and allows engineers to focus on higher value tasks instead of being bogged down by trivial alerts of outdated information. Finally, 3.8 times faster solution generation is where all the previous points come together. By having accurate contextual knowledge embedded in their workflows, engineers can diagnose problem faster, implement solution faster, and innovate faster. A task that might have taken a team hours or even days or can now be completed in a fraction of time. This acceleration of problem solving translates directly to better uptime, faster product releases, and more efficient teams. These metrics show that knowledge ecosystems are not just a theoretical improvement, they deliver measurable, tangible benefits. They allow organizations to scale their engineering operations while keeping quality and accuracy high. They also show that AI is not replacing humans, it is augmenting human capabilities, allowing engineers to focus on critical thinking, creativity, and decision making rather than repeating data sifting. Cognitive augmentation modes. Now that we have seen the real world impact of knowledge system, let's dive into one of the most exciting aspects, cognitive augmentation modes. This is where the system goes beyond simply storing or organizing knowledge. It actually enhances human thinking. And there are four modes: attentional, analytical, memory, and creative. Each of these modes corresponds to different aspects of human cognition. Together, they extend what engineers can do, allowing them to focus, analyze, remember, and innovate far more effectively than with traditional systems. Let's start with attentional augmentation. In a typical engineering environment, teams face hundreds or thousands of alerts, logs, and updates every day. This constant influx creates cognitive noise. It's easy to miss the most important signal because you are overwhelmed. Attentional augmentation filters out irrelevant information and highlights the priority items so engineers can focus on what truly matters. Imagine incident management instead of being distracted by dozens of minor alerts. The system brings the critical issues front and center, allowing for faster and more precise responses. Analytical augmentation is the system that acts as a powerful co-pilot for reasoning. By applying AI and ML to large streams of events, logs, or telemetry data, it identifies patterns, anomalies, and relationships that might be impossible to spot manually. It supports hypothesis testing and helps prevent failures before they occur. Engineers are no longer just reacting to problems. Instead, they are proactively making data-driven decisions that minimizes work, risk. Memory augmentation is one of the biggest challenges in engineering is as this is knowledge retention. Teams often reinvent solution because past work is not easily accessible. Memory augmentation ensures that all contextual knowledge, past experiments, resolve issues, design patterns, and troubleshooting steps is preserved and retrievable on demand. This is not only reduces duplication of effort but also accelerates onboarding and ensures organizational continuity, making sure no insights gets lost over time. The creative augmentation mode goes beyond support. It helps engineers innovate and iterate by combining existing services, design patterns, and data in novel ways. The system can suggest solutions or approaches that humans might have thought of alone. It's like having a co-creator that can inspire new ideas, spark innovative architectures, or suggest integrations that push the boundaries of what's possible. The beauty of these four modes working together is that they extend human performance in a balanced and a complementary way. Attentional augmentation keeps focus, analytical augmentation improves reasoning, memory augmentation preserves knowledge, and creative augmentation expands innovation. In practical terms, this means engineers are not just more productive, they are smarter, faster, and more capable of solving complex problems. By augmentation and human cognition acts across these four dimensions, organizations can unlock performance levels that were previously impossible, creating a culture of continuous improvement, learning, and innovation. Let's discuss in detail of each augmentation. So, attentional augmentation. This mode is all about helping engineers focus on what truly matters by filtering out unnecessary noise. In today's engineering and cloud environments, professionals are constantly bombarded with alerts, notifications, logs, and updates. Without a proper system, it's extremely easy to miss critical information or get distracted by irrelevant data, which can lead to delays, errors, or even failures in the complex systems. Attentional augmentation tackles this problem by prioritizing and highlighting the most important items. Think of it like having a smart filter that swifts through thousands of incoming signals in real time and only surfaces what is actionable or high priority. Attentional augmentation changes this by bringing the critical alerts to the top, suppressing the minor ones, and giving the team a clear view of where to focus first. But this is not just about removing noise, it also contextualizes prioritization. The system understands the context of each engineer's role, current projects, and system dependencies. So the alerts and information surface are tailored to what matters for that specific user or team, reducing the mental load and improving response times. For example, a DevOps engineer may see infrastructure relating incident prioritized, while a data engineer receives alerts tied to ETL pipelines failures or anomalies in data flows. This ensures that engineers are always looking at the right signals for their work. Another benefit is in incident resolution and productivity. When focus is optimized, engineers spend less time hunting for relevant information or deciding what to ignore. This can dramatically reduces downtime and accelerate problem solving. It also reduces errors caused by fatigue or cognitive overload. Because engineers are not being distracted by dozens of low priority messages at once, attentional augmentation especially acts as cognitive filter and assistant, helping humans directly their attention where it's most impactful. In the broader knowledge ecosystem, this layer works hand in hand with analytical memory and creative augmentation to ensure that engineers are not just faster but also smarter and more strategic in their actions. Analytical augmentation. If attentional augmentation helps us focus on what matters, the analytical augmentation helps us understand why it matters and what might happen next. In simple terms, this mode uses AI to find hidden patterns, support hypothesis testing, and prevent failures proactively. It's about turning large, complex data into insights that humans can act on with confidence. Modern cloud systems generate massive volumes of data, logs, metrics, telemetry, transactions, and sensor readings. For a human, even an expert, it's impossible to manually sift through all the data and find relationships or trends. Analytical augmentation changes that by applying advanced algorithms, things like anomaly detection, clustering, correlation analysis, and time series forecasting to uncover insights that might otherwise go unnoticed. For example, let's say you are running a large scale cloud infrastructure and you start seeing intermittent latency spikes. A traditional monitoring system might show the spikes, but not explain why they are happening. Analytical augmentation digs deeper. It might find that these spikes always occur after a certain deployment or when a specific service exceeds its memory threshold. This kind of correlation helps engineers identify the root cause faster and more importantly before it becomes a major incident. Supporting hypothesis testing in engineering, we often form assumptions. Maybe this configuration caused the issue, or maybe the new data source is slowing the system down. Analytical augmentation helps validate or reject those hypotheses quickly. It's like having a digital co-analyst that can test scenarios, run simulations, or replay historical data to confirm or disprove your assumptions. This makes the decision making process more evidence based and less about guesswork. Then we come to proactive failure preventations, where we wait for something to break, then fix it. Analytical augmentation changes that model. By continuously scanning data streams for patterns that precedes known issues, the system can alert teams before failures happen. For example, it can detect early warning signs like gradual performance degradation or small configuration drifts that could cascade into large outages if ignored. Let's take a real world scenario. Imagine a data pipeline that starts showing a slow increase in processing time every night. Humans might not notice it immediately, but an analytical augmentation system can identify that pattern, recognize it matches the past cases where a certain API started throttling, and notify engineers early so they can fix it before the pipeline fails. The big advantage here is speed and foresight. Engineers gain the ability to anticipate and act, not just respond. This means fewer outages, better system health, and more predictive performance. Think about this in the context of entire knowledge ecosystem. Analytical augmentation acts as a brain of the system, constantly analyzing data, learning from history, and offering data-backed guidance. When combined with attentional augmentation, it ensures that not only are we focusing on the right things, but we also understand them deeply and act intelligently. Memory augmentation. This one helps remember and reuse what we already know, preserves contextual knowledge, retrieves histories on demand, reduces duplication of efforts. That's really the essence of this layer. It ensures that the lessons, experiences, and insights of the past are not lost or forgotten, but instead available instantly when needed. Let's think about this from an engineer's point of view. How often have we faced a problem that someone else in the team had already solved 6 months ago, but we just didn't know? Maybe it was documented in a wiki, maybe buried in an email thread, or maybe the person left the company. So we end up spending days reinventing the wheel, repeating the work, retesting fixes, or rediscovering design patterns that already existed. Memory augmentation changes that. It acts like a collective organizational memory where every event, solution, and insight is automatically captured, contextualized, and stored in a searchable way. But it's not just about archiving documents, it's about contextual recall. Meaning, when you search or query, the system does not just pull text matches, it understands what you're asking and retrieves relevant knowledge based on meaning, not keywords. Here's an example. Imagine you are an engineer working on optimizing a data ingestion pipeline. You type into your conversational interface. Has anyone optimized high latency pipelines on Azure Data Factory? A memory augmentation system does not just show random documents with these words. It can retrieve prior solutions, the code snippets used, who implemented them, and what outcomes were observed. It can even summarize lessons learned or compare multiple past approaches. This kind of memory enables organizations to learn once, apply many times. Every solved incident, every completed project, and every experiment feeds back into the system, enriching the shared knowledge base. Another key part is preserving context. When humans recall information, we don't just remember the fact, we remember the situation, the problem, the constraints, and the reasoning behind it. Memory augmentation does the same. It stores not just the solution but also the conditions under which it was applied, like environment configurations, dependencies, and data patterns. So when the system recalls it, it can tell you why something worked in one case and whether it applies to your current situation. Over time, this builds organizational continuity. New employees can get up to speed faster. Teams don't lose expertise. When people move roles, institutional knowledge compounds instead of fading. It's like having an engineer who never forgets and can instantly brief anyone on what's been tried before. And there's also a major productivity gain because engineers spend less time searching for answers or duplicating work, they can focus more on innovation. Some organizations that use memory augmented systems report 20 to 30% reductions in time spent troubleshooting or repeating previous tasks. That's real measurable efficiency. So, to summarize, memory augmentation is about preserving contextual knowledge, retrieving histories on demand, and reducing duplication of effort. It turns knowledge from something static and scattered into a living, evolving resource that grows with every interaction. Creative augmentation. It generates new design ideas, suggests novel integrations, enhance innovation capacity. This mode represents the shift from AI as a passive assistant to AI as an active co-creator, helping engineers and teams to design, imagine, and build in ways that go beyond what humans alone might conceive. Even the best engineers or architects can get stuck in pattern using the same design templates, technologies, or problem solving methods over time. Innovation slows because people subconsciously repeat what has worked before. But AI systems trained on large and diverse data sets can break that limitation. They can combine ideas across domains. For example, connect cloud deployment strategy from finance to data governance model in healthcare to spark unexpected possibilities. Suggest novel integrations. This is where creativity really shows its value. In modern cloud ecosystems, tools are modular. You have data lakes, AI services, APIs, and automation workflows, but figuring out how they can work together for new outcomes can be overwhelming. A creative augmentation system can automatically discover logical combinations between these systems. For example, it might connect telemetry data from Azure Monitor to anomaly detection models in Fabrics, then route those insights into Power BI dashboards, all suggested automatically. Collaborative creativity is where AI does not replace human imaginations but enhances it. When engineers brainstorm with an AI model, they get rapid interactions and iterations, comparisons, and variations. For instance, if a data architect says, design a scalable pipeline for IoT analytics, the system might instantly generate multiple designs, one optimized for latency, one for cost, and one for redundancy. And this is where the phrase enhance innovation capacity comes in. Innovation capacity is not just about productivity, producing more ideas, it's about creating better ideas faster. When teams can afford the repetitive and combinational parts of design to AI, they gain more cognitive bandwidth for strategic thinking and experiment. Another real world impact of creative augmentation is cross domain innovation. AI does not care about departmental boundaries. It can take insights from DevOps, logs, user experience data, and financial trends all at once. That means it can propose connections humans might not see, like how customer support chat patterns could inform product telemetry priorities. So, in a summary, creative augmentation is not about replacing human creativity, it's about scaling it. It helps regenerate new design ideas, suggest novel integration across complex systems, strengthens innovation capacity by giving teams tools that think with them, not just for them. AI can enhance creativity and innovation, governance and ethics. It's equally important to address how we govern these systems responsibly because a powerful as AI driven knowledge ecosystem can be, their success depends entirely on trust in fairness, privacy, and human control. 68.9% fairness improvements with interventions, 83.4% privacy, risk reduction via federated learning, safeguards for cognitive autonomy. In AI system, fairness means ensuring that insights and decisions are unbiased, that they don't favor one group, dataset, or outcome over another. When we say 68.9% fairness improvements with interventions, it refers to measurable gains achieved through AI fairness, auditing techniques, things like bias detection, rebalancing training data, and introducing explainability layers. Risk reduction, which is 83.4% via federated learning. Privacy is a cornerstone of trust. Engineers work with sensitive operational data, logs, models, customer configurations, and traditional centralized learning approaches can risk exposing it. Federated learning solves this by allowing AI models to train collaboratively across distributed systems without moving the raw data. This drastically reduces privacy risk and regulatory exposure, all while still allowing the ecosystem to learn from real world use. Safeguards for cognitive autonomy. This is perhaps the most philosophical, but it's crucial. Cognitive autonomy means ensuring that humans remain final authority, the decision makers, even when AI provides recommendations. In other words, AI supports human reasoning, it does not replace it. Think of it like having an extremely capable advisor. That's the foundation of ethical AI, augmented intelligence, not artificial control. So to sum up, the governance and ethics layer is not just safety net, it's a strategic enabler. By achieving nearly 70% fairness improvement or 80% privacy risk reduction and enforcing safeguards for human autonomy, the ecosystem ensures that innovation remains ethical, explainable, and human centered. Embedding into Microsoft Fabric. Let's talk about how all these ideas come to life without real world platform. Microsoft Fabric is a unified data and analytics platform that brings together data movement, data engineering, data science, real-time analytics, and business intelligence under one ecosystem. Think of it as a data backbone that connects everything from raw data in your lakehouse to polished insights in Power BI. Fabric is built on three key strengths: the lakehouse architecture, which merges the flexibility of data lakes with the structure of warehouse, enabling both raw and curated data to live together. AI integration, which allows data to, to be not just stored and queried, but continuously analyzed, summarized, and understood using advanced machine learning models. And finally, governance ensuring that data remains compliant, secure, and auditable across all layers. The lakehouse provides the data for foundation, integrating through APIs and copilots. This is where the user experience really changes. APIs or application programming interface allow system to talk to each other seamlessly. By exposing APIs, the knowledge ecosystem can plug into any part of Microsoft Fabric, whether it's a pipeline in Synapse, a notebook in Data Factory, or a Power BI dashboard. Third, driving sustainable innovation loops. This is the real payoff. When we embed knowledge ecosystem into Microsoft Fabrics, innovation stops being a one-time project and become a continuous leap. The loop works. Engineers perform work and generate data, new design code, logs, or insights. The ecosystem captures and processes that data in real time, learning from every action. Those learnings are fed back into the fabric, enriching future workflows with smarter recommendations and predictive insights. As more users interact and the system keeps evolving, getting better, faster, and more accurate. These feedback loops means innovation becomes self-sustaining. And because it's built within Fabric, scalability and reliability comes built in. Fabric handles enterprise scale enterprise scale workloads, compliance requirements, and global access so the knowledge ecosystem can focus entirely on improving the intelligence layer rather than rebuilding infrastructure. Embedding into Microsoft Fabrics brings everything together. It aligns perfectly with Fabric's Lakehouse, AI, and governance pillars. It integrates directly through APIs and copilots, ensuring effortless user interaction, and it enables sustainable innovation loops, a system that continuously learns, adapts, and improves. With Fabrics as the backbone, knowledge ecosystem don't just support innovation, they become the engine that drives it. They make continuous learning practical, scalable, and deeply embedded in how modern engineering actually happens every day. So, the key takeaways are knowledge decay is real. The half life of technical knowledge keeps shrinking, so static systems can't keep up. The second is AI native ecosystems are essential. They continuously capture, process, and distribute knowledge. The four layer architecture: foundation, processing, interaction, integration ensures scalability, resilience, and speed. Cognitive augmentation empowers engineers to focus better, analyze faster, remember more, and innovate smarter. And the last is trust equals fairness, privacy, and autonomy. Without these, no system can sustain long term success. The ultimate takeaway: continuous innovation in cloud engineering demands not just better tools, but a smarter learning ecosystem. AI keeps knowledge alive, relevant, and immediately usable, turning information overload into strategic advantage. With this, we come to the end of our session. As I said earlier in my initial start of this session, please connect with me on LinkedIn. Let me know your thoughts and feedback. And if you have any questions, please feel free to reach out to me over LinkedIn. And thank you so much for joining my session.